heterogeneous and homogeneous equilibrium. So the chemical equilibrium can be classified according to the physical state of the reactants and the products present. So in homogeneous equilibrium, what do you guys think that's going to be? Think about homogeneous versus heterogeneous mixture. What does that mean? Say that one more time. All the reactants and products in this equilibrium are going to be in the same physical state, meaning they're all going to be in the gas state or liquid state or solid state or the aqueous phase, right? So all components of the reaction will be in the same physical state. So in this example here, this would be a homogeneous equilibrium, right? The reaction is going back and forth. It's a reversible reaction. And then everything here is in the gas phase, right? They're all in the gas phase. So that's a homogeneous equilibrium. And then by contrast, a heterogeneous equilibrium, what do you guys think that's going to be?
Different states.
They'll be in different states, right? So it's one, it's the other. So let you guys finish writing this before I go home. And so this is going to become important because if you're in different states of matter, then only some of them are going to contribute to the equilibrium constant. So in heterogeneous equilibrium, we have components that are in different states of matter. Okay, so here we have two components that are solid and two components that are gaseous. And so what we can start thinking about is why do some affect the equilibrium more than others? Well, if we think about a solid's density, right, as more of the solid, is created or consumed, the relative volume doesn't change, so the molar concentration of that solid isn't going to change, right? So solids and liquids have very high densities, so the molar concentration isn't going to change much as we look at solids or liquids as the reaction reaches equilibrium. So once we have an equilibrium ratio, adding more of that solid or less of that solid doesn't change the overall volume of the system very much, so it's not going to change the equilibrium. And so the next lab that we do is going to be dealing with finding equilibrium constants for a mixed heterogeneous equilibrium, because we can take advantage of this to then solve for an equilibrium constant. And the way that it's expressed with solids and gases is that our original equilibrium constant is equal to the ratio of the products. So this would be H2 to the power 4, Fe3O4, so iron 3 oxide, over iron, which is also going to be solid, raised to the power of 3, H2O to the power of 4, is that if we add more solid to this system, right, the ratio has to stay the same. But as we add more solid to the system, that's not changing the overall molar concentrations of anything else in the system because the volume itself isn't changing. So these two, this ratio here, is a constant value. And so we can then rewrite this as Fe3O4 over Fe3 times H2 4 over H2O 4. And since that's a constant value, we just absorb it into the equilibrium constant. So we just indicate that that's some adjusted value for the actual equilibrium constant, where that's just equal to the original equilibrium constant divided by or multiplied by the inverse of whatever this ratio of solids is in our solution or our mixture. Right, so because this ratio is constant, as we add more or less of iron 3 oxide in iron, elemental iron to the system, it's not going to shift the equilibrium in either direction, right? Because the density of those are so high, so as they react and form the other ones, it doesn't really change the molar concentrations of anything else. So that means that the gases in the aqueous molecules are really what's going to determine the equilibrium constant. And so we kind of just treat this as the equilibrium constant. When we have these heterogeneous equilibriums. So that's kind of the algebra that we do to get to that, but this is really just here, nice and color coded, right? We just treat the equilibrium as some constant adjusted equilibrium constant, right? So really only gases and aqueous species contribute to equilibrium. That's kind of the main takeaway, right? So we just treat the equilibrium constant. If I said write the equilibrium constant for this reaction, you would just write this right here. You would ignore solids, liquids. We ignore solids, liquids, and solvents. The only time you might consider that is in extremely concentrated solutions. You can include solvents in there. It has to be very, very concentrated for that. And so here's just a little pictorial representation. As we add more solid to the system, it doesn't shift the equilibrium of these gases in either direction. Why? Because the change in volume when we go from one solid to the other is so small compared to the change in volume for the gases. Because solids tend to be, and liquids tend to be so much denser, right? So that's what the reasoning for why we don't include liquids and solids in the expression for the equilibrium. They just don't affect the relative amounts of the gases or the aqueous species in the mixture. Okay. So how would you identify this reaction? Would you identify it as homogeneous, heterogeneous, and write the expression for Kc for this reaction? So you have iron 2 oxide and then iron hydrogen gas to form water vapor for this equilibrium. Heterogeneous or homogeneous? Heterogeneous, right, because we have 2 solids and then 2 gas molecules, so it should be a heterogeneous equilibrium. And then what's the equilibrium constant for this reaction then? Yep, just the concentration of the gases, right? And they both have a stoichiometric coefficient of 1, so this is all that we include for this mixture. Right, so I know it seems simple, but when we're doing ice tables or looking at, changes of concentrations on the way to equilibrium, we have to make sure that we don't include the solids or liquids in our expressions for the equilibrium constant. Remember, we use this equilibrium constant to solve for equilibrium concentrations last week or on Tuesday with that simple example. So we're going to do a lot more of that, so it's important to be able to just identify the equilibrium constant relatively quick. Okay, and what about for this equation? Here we have everything is in what phase? Gas phase, right? So that would be classified as what kind of equilibrium? Homogeneous. And then Kc would just be the ratio of what? How many different molecular species are going to go into our expression for the equilibrium constant? Yeah, so we should have 4 total in there, right? So this would be H2O, carbon disulfide, H2S, and then CH4. So am I missing anything here? The exponents, right? We need to have our stoichiometric coefficients and our exponents. Right, so relatively straightforward, but important that we're careful with how we do this. And so this is the next example is a similar one to what we might do in lab, where if we can control or can influence the fact that there's only one non-liquid or solid in the reaction, like in this titanium tetrachloride synthesis, then the equilibrium constant should have how many terms in it? Just one, right? And so if you can find the equilibrium constant of a reaction like this, you can then solve for, or you can find the equilibrium concentrations. You can get the equilibrium constant from that lone concentration. So this is then going to be 1 over, right? Because the products and the reactants go in the denominator, chlorine gas raised to the power of 2, right? And then this would be a heterogeneous equilibrium because we have mixed phases here, right? So even though we have both solid and liquid, both of them are excluded from. There's no hierarchy, it's just aqueous and gas phase molecules that go in the equilibrium constant. All right, so that's how we deal with heterogeneous equilibrium, which also means that if we have mixed heterogeneous equilibrium and differing number of moles of gas on either side, there's also that condition where Kp and Kc are going to be equal to each other. And it only depends on the specific molecules that are in those expressions. So it's going to be liquid, or not liquids, aqueous or gaseous molecules. Okay, so for these 3 reactions, which of these reactions does Kp equal Kc? So think for a second what conditions you needed for those to equal each other. So which of these do you guys think Kp and Kc are going to be equal to each other? B. And why B?
Because the exponents cancel out.
Because exponents, right, the condition was when we had delta N, which was the sum of the moles of the product, minus delta Ni for the reactants. When this is equal to 0, that's when Kp equals Kc, right? So the difference in the moles of the products minus the reactants. But what else do we have to consider here when we look at this? Right, because at first observation of B, it looks like we have 4 on the reactant side and then 5 on the product side. So why is that not the case? Why would those two equilibrium constants be equal to each other here? Yep, because we only count for the gases, right? So this is only counting for gases. Right, and that follows with what we said earlier. The solids and liquids don't affect the position or the relative amounts of, in that example, it was carbon monoxide and carbon dioxide. Right, so all that matters is the moles of gases. So we have 3 moles of gas on the reactant side, and also 3 moles of gas on the product side. And so this is the only one that meets those conditions. The first one, the moles of gas are not equal to each other, and the total moles are unequal to each other. And the third one, the same thing. Third one, we only have 1 mole of gas on the right-hand side and 0 on the left. Right, so that's when we know Kp and Kc are going to be equal to each other, especially when we have these mixed equilibrium systems or heterogeneous or homogeneous equilibriums. All right, any questions on that? Good. Okay, so now we'll get into calculations for Kc, which will then lead us to calculations for equilibrium concentrations. So the most direct way to obtain an experimental value for the equilibrium constant is to measure the what of reactants and products in a reaction mixture at equilibrium. So what did you guys do in your most recent lab? What was the end goal of your guys' lab? What were you trying to calculate? You wanted to calculate the equilibrium constant, right? And how did you do that? What did you directly measure? The changes in the height of the solutions, right? And that allowed you to find what? Concentrations, right? So we find the concentrations of the reactants and the products, right? Once you knew the concentration of the product in solution, which you found by looking at the change in color with the change in height, then you knew the concentration of the reactants at equilibrium, right? And that's why we had to have the standard solution again, is because we needed something to compare to with a known concentration, whereas the equilibrium concentrations you don't know beforehand, right? You don't know what the equilibrium constant is, so how are you supposed to know what the equilibrium concentrations are? And so you use that to then find the equilibrium concentrations, and then that allows you just to solve for the equilibrium constant. You need it for 5 different solutions so that you can get an average equilibrium constant, right? Because the equilibrium constant, does it change depending on the initial concentrations of your reaction mixtures? Right, so does Kc change with initial concentrations? What do you guys think? For each of your guys' reaction test tubes, did you start with the same amount of stuff or did you have different amount of stuff for each of them? Different, right? And you were supposed to average all of your equilibrium constants together. Do you think they're supposed to be close together or far apart? Close together, right? So you should get the same equilibrium constant no matter what initial conditions you start with. Why? Because it doesn't matter what the initial concentrations are, just what the ratio of the concentrations are at equilibrium, right? So Kc does not change with initial concentrations. And so that was the purpose of solving for the equilibrium concentration, was then to find the equilibrium constant. And we'll learn that the equilibrium constant is then related to other thermodynamic properties like the energy of the reaction and how the temperature affects it as well. So if at equilibrium the concentrations are shown below, then what would the value of this equilibrium constant be? So what did you guys ultimately plug in to solve for the equilibrium constant? I know we just used an Excel sheet, but this was the last step, right? What is Kc equal to, right? These are the equilibrium concentrations. Yep, that's right. So for Kc, it's just equal to Hi squared over 0. I'll do variables first, H2, I2. They're all in the same phase, which means it's what kind of equilibrium? Yep, homogeneous equilibrium. So everything goes in the equilibrium constant. And so we just plug in these values. We get 0.78 molarity squared over 0.11, 0.11. So if you plug that in, you just get a value for the equilibrium concentration. So the equilibrium constant, for the equilibrium constant. The equilibrium concentrations are what we're usually going to be solving for. Where did my calculator go? 0.78 squared divided by 0.11 squared. So this should be about 50.3 is what this equilibrium constant should be. So when we're actually solving for the equilibrium constant, all we're doing is we're plugging in the equilibrium concentrations into our expression. Oops. And so just to reiterate, for any reaction, the equilibrium concentrations of the reactants and products depend on what? Right. So the equilibrium concentrations can be different or the same at equilibrium, depending on the initial concentrations. Say that again? So the physical state does affect the equilibrium constant, right? But if we have, let's say we have all a homogeneous equilibrium, right? Do the concentrations at equilibrium always have to be the same? All right, so if this is our expression, Kc B over A. Do those two values for A and B, right, these are the equilibrium concentrations, have to be the same? No, so when would those be different from each other? What do we think about it in terms of, our concentration versus time? We have the concentration of A, and then in B we have the concentration, in purple we have the concentration of B, right? So initially, we're going from A to B. Say A, we start with some amount. Oops. Too far back. We start with some amount of A, that goes down till we reach equilibrium. And then B, we go up till we reach equilibrium. Right, we're saying, you guys said that the concentrations at equilibrium don't have to be the same, right? But what do the concentrations at equilibrium depend on? Time, right? They do depend on time, right? If you look early in the reaction. Once we reach equilibrium, right, it's not changing with time anymore. But before that, where do we start? What was that? The initial concentrations, right? So it depends on the initial concentrations of each species. The initial concentrations. Right? Because we don't have to have the same value at equilibrium. All that matters is that we have the same ratio of them at equilibrium. So if we start at a different spot, right, maybe here, and maybe B started here, right, we don't start at 0, maybe that just goes down a little bit or something like that, right? So the actual values, meaning where these lines are in each different experiment, those are different from each other, but even you take the ratio of those values, those stay the same. So that's one thing that affects our equilibrium constant, right? And so at a given, what is another thing that can affect the equilibrium constant? The temperature, right? So the other thing that can affect it is the temperature. So when we have a given temperature, the equilibrium constant stays the same. So Kc stays the same. Right, so again, it's not the initial concentrations that are important for the equilibrium constant, value, but it does tell us what the values of the concentrations will be at equilibrium. And the thing that remains constant is the ratio of those concentrations. And so as long as it's given at the same temperature, then you should have that same ratio no matter what. And that's what I mean eventually when we talk about thermodynamics, how temperature will come into play into affecting the equilibrium constant. Okay, so here's kind of just a tabulated expression of that, right? So here we start with different initial concentrations. So this looks a lot like your guys' test tube, right? Test tube 1 through 5 here. So you're given a bunch of different initial concentrations. They have different equilibrium concentrations for each trial, right? So all of these values are different. But when you plug them into the equilibrium constant, right? Plugging these concentrations in here, the ratio stays the same for all of them. So that's why you guys got some statistical data for your lab, because you do it for a bunch of different initial concentrations, but you know whatever the ratio is, after you find those equilibrium concentrations, should stay the same. So that's why you average them together. Okay, and so where we're gonna pick up on a week from now, after the exam, is when they're not given, you can look at where you start, what the change is, and then solve for equilibrium concentrations. And so oftentimes, if you don't know the initial amounts of either reaction, and you don't know how much is created, I mean, you can't, we could measure the final concentration because we had something directly to compare it to, right? But what if you're looking at a reaction that doesn't change with color, and there's no direct way to measure what the equilibrium concentration is? Then you're gonna have to go based off of how much you think is gonna change. You define that change as some variable x, and then solve for this if you have a given or a known equilibrium constant. Okay, so we'll start with that next time, and so this kind of brings up ice tables, which if you guys have heard of before is usually the bane of Chem 1B or second semester general chemistry, right? So we do ice tables for a long time. Like next probably month or so, we'll be doing ice tables for regular equilibrium reactions, and then we'll talk about acid-base equilibrium, and so on and so forth. All right, so we'll end that here today.